Fine now?
Yes, sir.
Yeah, fine. So now these three things, I don't know whether you have studied these three or not. At least two, you should be aware of these two. Photoelectric effect and characteristic X-rays, you should be knowing, right? The Compton effect is the other one of the phenomena where we see a light ray incident on an atom or a material and it gets diffracted, right, or scattered, right? So the scattered light ray will have a different wavelength than the incident one. Okay, let's say a light ray of 500 nanometer incidents on a material and it gets scattered. When it gets scattered, its wavelength is more than the incident one. That means its energy is less than the incident one. So it has lost some of the energy. Where did this energy go? This energy has lost this energy when it interacts with an electron in the material. That means electron has absorbed fraction of the energy, not full, fraction of the energy. Okay, so this, to explain this particular phenomena, that is the Compton effect, the only way we could think of is light ray and the electron. These two are interacting. Light is a wave, electron is a particle. Right. The only way we could explain it was by considering collision between light ray and electron. See, light is a wave, electron is a particle. The only way of interaction we could understand or explain the fact was through the collision. So when I say a collision between a light ray and an electron, it doesn't make any sense. There is no meaning for it, right? Then we will have to consider, of course, electron is a particle that we know it has mass. What about the light wave? Yes. So here,
in photoelectric effect also, light will fall on metal surface and electron is ejected, sir.
Electron is ejected. Here, electron is not ejected. There is interaction between light ray and electron. Light ray continues to travel, but with a higher frequency or lesser energy. Light ray
you
still
tell the
continues
definition,
to travel.
sir. We can note
In
down.
I'll tell you. First, you understand the concept. Okay.
Then we are telling about Compton effect, right?
Compton effect, because you know the photoelectric effect, right? I'm explaining you the Compton effect. Try to understand. Okay. So here, what happens? Okay, let me take this. Let's say here there is an electron in a material. There is a light ray. Incidents or interacts with this electron. This light ray has wavelength lambda. After the interaction, a light ray gets scattered with a wavelength lambda dash. Now this wavelength lambda dash is greater than lambda. That means lambda dash has lesser energy than lambda, right? Scattered wave has less energy than the incident wave. Yes or no?
Yes, sir.
Yes, sir. That you understand. So, okay. Now, where did this difference in energy go? Let's consider this as E incident and consider this as E scattered.
So absorbed by the particle?
Yes, exactly. So now this difference.
What is the lambda dash, sir? Which value, sir, that is?
Lambda dash is the same light ray is continuing, but with a different wavelength. Let's say this has 500. Let's say this has 500 nanometer. Okay. Okay. So here it is continuing the same light ray. Now it has 510 nanometer.
Sir, means it is the same light wavelength only, sir.
Yes, same wavelength. No, it is not same wavelength. Same light ray, but wavelength is different.
Means it reflected, sir.
Scattered. Right. So when it's scattered, it is scattering with higher lambda. Therefore, there is a difference in energy of the incident and the energy of the scattered. Okay, where did this difference energy go to? This difference energy would be absorbed by the electron. This difference energy would be absorbed by the electron and electron moves in this direction. Okay, so here this incident light and the electron are interacting. After the interaction, light ray loses some energy. That energy, that particular energy, whatever is lost, that is absorbed by the electron, and the electron moves from its place. This electron is considered to be free electron. Okay, so now the fact is, how do you account for this interaction? That is the thing. See, this electron is not absorbing the full energy of the wave. It is only absorbing a small fraction of the energy. Rest of the energy is continuing. Then how to account for this interaction? What type of interaction is this? All we know all these days is when a light ray incidents on an atom or interacts with an electron, that light ray is completely absorbed. That's what we know in photoelectric effect. But here only partially it is being absorbed and light ray is continuing. So how to account for this partial? So here we bring in the concept of collision. See, in collision, the energy exchange can be anything. Whatever the fraction you want, you can take in collision, right? So here we have to consider the fact that, or concept that, there is collision between the incident light ray and the electron. So now we call this incident light ray as photon. Instead of light ray, now we will call it as photon because we are considering collision. So collision has to be between the particles. And this incident light ray will be considered as photon, and it has a momentum. Okay, so there is a collision between the incident photon and the electron. When I say there is a collision between the incident photon and electron, photon becomes a particle or is considered as a particle. Right?
So electron is at rest, or it is also moving?
Electron is at rest. It can be at rest or it can be moving. Most of the time we consider it to be at rest. It is a free electron. Okay, it need not be at rest. Okay, still it takes that energy. That's it. Okay, the fact is what we have to stress here is there is collision between these two particles, that is photon and the electron. That means the light ray behaves as a particle in this particular phenomena. In this particular phenomena, light ray behaves as particle. Point number one. Then in photoelectric effect also, see, there is a basic definition for waves, right? What is the basic definition? Basic characteristics. Waves carry the energy from one point to another point, source to destination, in a continuous manner, and the energy is deposited in a continuous manner. Do you remember? Energy is carried or transmitted and deposited in a continuous manner. That is the basic characteristics of waves. But in photoelectric effect, what we see, if there is an electron and it has some binding energy, or what is that energy we call? The electron's energy? Threshold energy, right? What is that energy we call? Electron, if it has to come out of the material.
Ionization energy.
Huh?
Ionization energy.
Not ionization energy. What do we call it?
The threshold only.
Threshold is
energy.
Threshold is with respect to what is that wave. But for electron, it is not binding energy. It is what is that? You just try to.
Energy.
Not excitation, because the electron will completely come out of the material. Excitation is within the material. Okay. Eventually, I'll tell in some time, or you just, if you remember, you just tell me. What is the energy required to take it out of the material? Okay. So here, for that, the incident photon needs to have some minimum frequency, which we call as threshold frequency. When we bring in this concept, that means the incident photon or the light ray should have minimum frequency. The basic definition, characteristic of the wave, that there is a continuous deposition of energy, we lose it, right? If an electron needs 5 electron volt to come out of the material, we need light rays of energy at least 5 electron volt. Any light ray less than 5 electron volt will not cause electrons to come out. That means the continuous deposition of energy is not helping in this time at this particular phenomena. Then what is the alternative explanation? That means here also we have to consider the fact that light ray consists of photon, and the photon of the minimum energy 5 electron volt, which corresponds to the energy of the electrons to come out. Only those photons can cause photoelectric effect, otherwise not. So here again comes the fact that light ray consists of photons of particular energy. So each these photons have quantized energies. They are packets of energies. They are quanta of energies, or they have quantized energies. And it is deposited at once. When it interacts with an electron, the whole of the energy is given in one instance, in the case of photoelectric effect. If it transferred in one instance, and if it is enough for the electron to overcome the binding energy and come out, then only electron comes out, otherwise not. So in two phenomena, photoelectric effect as well as Compton effect, we have to consider the particle nature of light, or the photonic nature of light, not the wave nature.
Sir?
Yes.
Is that energy called?
Yes, sorry. Yes, exactly. Thank you very much. That energy is called as work function. It is not ionization energy. Ionization energy corresponds to single atoms. Work function corresponds to the material as a whole. So that is called as work function. Right. So the photon energy is more than the work function, equal or more than the work function, then only electrons comes out, otherwise not. Okay. So two phenomena.
Give the definition for Compton effect, sir.
I will tell you. So the two phenomena tells us that light rays consist of photons of discrete energies. So the basic definition of photon comes out to be the packets of energy.
Effect and Compton effect.
Both.
Yeah.
Right. Then in the case of characteristics X-rays, what do we see in characteristics X-rays?
Electrons target the tungsten material, so the X-rays come out. Photons come out.
High energy electrons are bombarded onto some materials. For example, tungsten, lead, and many others are there. So those high energy electrons knock off the core electrons. When they knock off the core electrons, electrons from the higher energy levels or outer orbitals, they de-excite to that core levels. Right? K-shell, normally K-shell. That core levels, core orbitals. And the difference in energy is emitted as characteristics X-rays. So till then, this discrete nature of electron arrangement in orbital was not explained or was not proposed. So when they see characteristic X-rays, it was a very clear evidence that the atoms has discrete orbitals where the electrons are located or distributed. And when these electrons de-excite, we get X-rays of a particular wavelength. We don't get continuous X-rays. We get X-rays of a particular wavelength. That means we get photons of a particular energy. So this again says that the light rays or the electromagnetic radiation have characteristic photons in them which carry a particular energies corresponding to that particular situation and phenomena. Right. Now you note down the definition of Compton effect, photoelectric effect, and X-ray characteristic X-rays. You know. Note down.
Sir?
Yes.
So what is the difference between threshold energy and work function?
See, threshold energy, when we say threshold energy, that corresponds to the wave. Okay.
Yes, sir.
That is the minimum energy that the wave should carry to liberate or eject an electron. Okay. When we talk about the work function, that maps to the energy of the electron.
Understood.
When the threshold energy and work function match, when they are equal, at that particular instance, electrons are ejected. Otherwise not. You understood, no?
Yes, sir. Thank you, sir.
Very good. So, in the first case, in photoelectric effect, threshold frequency nu minimum is required for ejection of photoelectron. Okay. In the second case, interaction between electromagnetic wave and electron is considered as collision. In the third case, characteristic X-ray is a non-classical effect. It is not a classical effect, it is a quantum effect. For a given accelerating potential of the electron. See, electrons are accelerated, that is, high energy electrons are bombarded onto a material. How do these electrons get the energy, high energy? They are accelerated. We use a potential to accelerate these electrons. Okay. And these X-rays, when for a particular given accelerating potential, X-rays had a wavelength greater than lambda minimum. All the X-rays which were emitted, characteristics X-rays, they were all had wavelength more than lambda minimum. Nothing can be less than lambda minimum. So this lambda minimum corresponds to accelerating potential. Okay. So now note down. In the case of what do you want? Shall I tell only this thing particular, or you want definition for Compton effect?
Definition.
Please.
We'll write definition for all the three.
Yes, sir.
Okay,
Yes, sir.
Write down. Photoelectric effect. One, electromagnetic radiations of certain frequency incident on a metal whose energy is more than the work function more than the work function. Electrons are ejected from the surface of the metal.
So work function means that metals threshold
Yes,
energy.
metals. Work function means metals. That is the electron work function of the metal. That corresponds to the metal.
That is only that electron energy.
Can you please repeat it, sir?
That's very difficult. I form the sentence as it is. No, I cannot repeat. You just read it. Wherever there is blank, I'll fill it. Okay. Don't
Incident on materials.
Incident on material whose energy is more than the work function of the material, comma, electrons are ejected from the surface of the material. Electrons are ejected from the surface of the material.
Sir, work function is the energy of electron, no, sir?
Yes.
Okay, sir.
Incident radiation energy should be more than the work function. Then only electrons are ejected. That is the meaning. Okay.
Okay, sir.
Okay. Second one, Compton effect. An electromagnetic wave gets scattered by a free electron in a material. An electromagnetic wave gets scattered. Write this. An electromagnetic wave of wavelength lambda. An electromagnetic wave of wavelength lambda gets scattered by a free electron in a material.
A metal, no, sir?
Metal. Right.
Sir, by a free electron?
In a metal. The wavelength of the scattered wave is more than the incident. Wavelength of the scattered wave is more than the incident.
Sir, how it is possible, sir? Means it should decrease or else it should remain same. How can it increase, sir?
See, when the wavelength increases, energy decreases. Wavelength is inversely proportional to energy.
Yes, sir. Yes, sir. Yes, sir.
In some case, it will also decrease. Don't worry. In Raman effect, it happens in both the ways. Okay, let's not discuss about it. It's not okay. What did I say? More than the incident one, right? Indicating, continue the same sentence. Indicating transfer of some energy to the electron. Indicating transfer of some energy to the electron.
That's it, sir.
Full stop. Stop. This phenomena could be explained. This phenomena could be explained by considering.
Sir?
This phenomena could be explained by considering electromagnetic wave consisting of photons which have particle nature. Electromagnetic wave to be consisting of photons which have particle nature and their collision with the electrons and their collision with the electrons. And their collision with the electrons. Okay.
Yes, sir. Sir, means
X-rays, I will not give the definition. You write down whatever is written here. Characteristic X-rays is a non-classical effect. For a given accelerating potential, X-rays at wavelength greater than lambda minimum. Yes, you are saying something.
sir, is the definition now needed for the third one, sir?
Definition not necessary. Will not be asked to definition. You just understand the fact. What
Means
we
just
observe
we
in
say
that
briefly, sir. Means not
briefly,
definition, just
characteristic.
explain.
No. Okay. Explanation you want or characteristic X-ray? What do you want?
Means what it is, means what is that, means, sir?
Characteristics. No. See, characteristics X-rays. What happens? No, you accelerate electrons and bombard them on a material. Okay. These electrons knock off the core electrons of that material. You are using one free electrons to knock off core electron of an atom. When the core electron of the atom comes out, the electrons from the you have next class at what time?
Sir, no class is there, sir. You can take extra 5 minutes or 10 minutes.
I'll continue till I explain this particular concept, right? It won't take too much time. Okay, fine.
Yes,
Yeah.
See, we have we have this atom, nucleus. Then we have orbitals, right? Okay. So within these orbitals, we have electrons, let's say. Electrons. Sorry, just two only. Okay.
So that one you didn't said in Compton effect definition. So delta is equal to ET minus ES.
That you want, you can write out. That will not be asked. Don't worry.
Once you say that line means I can write it. Sir.
What is that?
Delta is equal to ET minus ES.
No, EI incident minus ES scattered. Energy of the incident light ray minus energy of the scattered light ray. Okay, so here we have an electron. Okay, we accelerate this electron and this electron hits this electron. When this electron is hit, this electron goes away. It goes out. So nothing is there. This becomes empty. When this is empty, an electron from the outer orbital will de-excite here. Sorry, straight line. I'm sorry, it should be straight line. Okay, an electron from the outer orbital de-excites. Okay. When it
we are
de-excites,
using one electron to move out another electron in another atom.
Electron. The incident atom also, the incident electron also goes away, and this electron which was here, that also goes away. Okay. So this will be empty space now, available for the occupation. So an electron from the outer orbital will de-excite. When it de-excites, it emits a gamma ray or an electromagnetic radiation. Okay, whose frequency or whose energy is difference of these two, difference between these two energy levels. Okay, when you plot this, this is the energy of the emitted radiation, electromagnetic. This is the intensity. What do you get? You get like this, right? Also some continuous. So this discrete nature or discrete energies of the emitted radiation, this is the emitted radiation, let's say nu. So this discrete nature of the emitted radiation was not expected. This is non-classical effect, right? When this electron comes down, it should not emit like this. First of all, this electron comes down and it has discrete orbitals. That concept itself was new. It was a quantum mechanical concept. The discrete orbital concept, it was quantum mechanical concept, right? So the discretization of the energy levels was first encountered with this characteristic X-rays and is a non-classical effect. So this also shows that the energy of the light is quantized. So the light waves do not have continuous energy. They have quantized energies and we call them as photons. That is what it says. Understand?
Sir, actually it needs more energy, no sir, the external electron.
Of course, it will have a lot of energy so that it knocks out.
But in the last point you have mentioned,
continues.
in last point you have mentioned X-ray have wavelength more than wavelength of minimum, no sir?
Yes. See, for example, let's say this particular electron has a, let's consider a hydrogen atom, right? What is the binding energy of the electron, 1s electron in hydrogen atom? Minus 13.6.
13.6, sir.
Yeah, remember, you should say minus 13.6 electron volt. So I will use some particular energy, that is electron volt E into V. V is the accelerating potential, E is the charge on the electron. So I use a particular voltage or the potential so that EV is equal to minus 13.6 or let's say 14, minus 14 electron volt. Sorry, plus 14 electron volt. EV is equal to, let's say, plus 14 electron volt. When I use this particular electron to hit this, right, this electron goes off, right? It takes this 14 electron volt and this goes off. This electron also eventually comes out somewhere. It will not stuck within the atom most of the time, right? Then this electron, outer orbital electron, it comes down and it emits energy. It emits energy. When it comes down, what is the maximum energy it can emit? If it is free electron somewhere here and if it de-excites, the maximum energy it can emit is, it was free. That means its energy was 0. When it comes here, what is its energy? When it comes here, what is its energy? Minus 13.6. That means it loses 13.6 electron volt. So when it loses 13.6 electron volt, that comes out as a gamma ray, an electromagnetic radiation, right? So that is the maximum wavelength. Sorry, that is the minimum wavelength it can have. If any other electron de-excites, they already are bound. They do not have 0 energy electron volt. They already should have minus 6 point something or minus 2 point, minus 1 point energy electron volt. So when they de-excite, always they will emit energy less than 13.6 electron volt.
Sir, means X-rays means the energy sending incidenting energy or incidenting waves energy, or which one's wavelength?
No. That is incident. What is incidenting is the electron. What you are getting is called as characteristics X-rays, and we are talking about this wavelength.
Sir, means the one last, it will come from outer orbit to inner orbit, that emits energy. That one is X-ray, sir.
Yes, that is X-ray.
But you said that is gamma ray, no, sir?
No, it is X-ray here. Sorry. Gamma means it is general. It has even higher energy, but here X-rays. It is X-rays.
Okay, sir. Sir, if you don't mind, at the last of class, will you define that one, sir, so that we can note down?
Which one?
Characteristic X-rays. This one you told us, sir, this process.
Oh, write down. High energy electrons high energy electrons incident on a material knocks off the core electrons. Knocks off the core electrons. Knocks off the core electrons.
So can you repeat, sir? Incident on the
High energy electrons incident on a material knocks off the core electrons of an atom. Core electron of atoms. Core electrons of atoms. Core electrons means either K or L shell only. Okay.
on metal, no, sir, not material, no, sir.
Yeah, no, need not metal here. Material.
Next point, sir.
Okay. Continue. Next sentence. Continue. Next sentence. These core orbitals are filled with the excitation of these core orbitals. These core orbitals are filled with de-excitation of these core orbitals are filled with de-excitation of electrons from the outer orbitals. Electron from the outer orbitals.
Sir, actually, the electrons in the outer shell will have more energy than the electrons in inner shell, no, sir.
You're right. They have more energy. When they come to the inner energy, they have less energy. As for inner orbital, they have less energy. Right?
Means they will lose energy, no, sir.
They will lose energy. They lose the energy in the form of X-rays. Right? No?
Sir. Next
Understood?
point, sir.
Next. Where did I?
Sir, electrons from outer orbitals. These core orbitals are filled
Outer
with.
orbitals are de-excited. They are filled with de-excitation of electrons from our outer orbitals. Right?
Sir.
The difference in orbital energy is emitted as characteristic X-rays for that particular type of atoms. The difference in orbital energies is emitted as characteristic X-rays for that particular type of atoms.
Characteristic X-rays?
For that particular type of atoms.
Yes, sir.
Okay.
Thank you, sir.
Okay. Next, continue. These X-rays indicated discrete nature of the light rays. Discrete nature of the light rays. Suggesting discrete nature of the light rays. Suggesting light to be consisting of light to be consisting of packets of energy called photons. Light to be consisting of packets of energy called photon. Okay, guys, fine then. We'll stop here. We'll continue day after tomorrow.
Sir.
Yes.
For this, is there no any equations, sir?